In the deep black of space, a single star burns so wide that light itself takes 9 hours just to cross its surface. Our entire sun would vanish inside it like a speck of dust dropped into an ocean. You're about to travel past stars that bleed metal into space, giants that pulse like beating hearts, and a hypergiant so massive it bends the laws of physics. If cosmic mysteries pull you in, hit subscribe and stay close. Some of these stars shouldn't exist. Some already died, and we're just now seeing it. Prepare yourselves. We begin. Step outside on a clear afternoon and look up. That blazing yellow disk you see, the one that warms your skin and lights your entire world, is a star. Our star. And for most of human history, we believed it was the center of everything. We were wrong about its size in the most embarrassing way. Our sun stretches about 865,000 miles across. You could line up 109 Earths across its face and still have room left over. If the sun were hollow, you could pack more than 1,000,000 Earths inside it. To us, standing on this small blue rock, those numbers feel impossibly huge. Here is the strange part. In the family of stars, our sun is considered small, almost forgettable. Picture a beach. Imagine every grain of sand on every shore on Earth. Now imagine each grain represents a star somewhere in the universe. Our sun would be one of the smaller, average grains, lost in a desert of giants. Some grains in this desert would be the size of basketballs, some the size of buildings, a few the size of cities. Astronomers measure stars using something called solar radii. One solar radius equals the distance from the sun's core to its surface. So when scientists say a star is 1,000 solar radii wide, they mean it could swallow our sun 1,000 times over in a straight line. The numbers we are about to explore will reach into the thousands, some past 2,000. The biggest known star pushes beyond 2,100 solar radii. To picture that scale, drop our sun next to it, and our sun becomes invisible, a pinhead next to a basketball. Our sun's true power comes from a tug of war happening at its center. Gravity pulls everything inward, crushing hydrogen atoms together with such force that they fuse into helium. This fusion releases energy. That energy pushes outward. The two forces balance, and the sun stays the size it is. Stars stay stable only as long as that balance holds. Some stars cheat. They burn so hot and so violently that the outward push wins and they swell. Others run out of hydrogen and start fusing heavier elements, which makes them puff up like a balloon filling with air. These swollen monsters are called giants and supergiants and hypergiants. The bigger they get, the more unstable they become. Our sun will one day join their ranks. In about 5 billion years, it will run low on hydrogen, swell into a red giant, and grow so large it will likely swallow Mercury, Venus, and possibly Earth itself. Even then, our future giant sun will look small compared to what already exists out there in the dark. Light from the sun reaches us in about 8 minutes. That feels fast. But the stars we are heading toward sit so far away that their light takes thousands, sometimes tens of thousands of years to reach our eyes. When you look at one of these giants in the night sky, you are looking at a snapshot from a time before written history. Some of those snapshots are already lies. The stars that sent them might already be dead. And the next star on our journey hides exactly that kind of secret in plain sight. Look toward the southern sky on a winter night and you will spot the brightest star anyone alive has ever seen. Sirius, the dog star, the diamond of the constellation Canis Major. Ancient Egyptians built calendars around it. Polynesian sailors steered ships by it. For thousands of years, Sirius held a sacred place in human imagination because nothing else in the night sky burned so fiercely. Astronomers were certain Sirius had to be a giant. Surely something so bright must be enormous. They were tricked. Sirius sits only about 8.5 light-years from Earth, making it one of our closest stellar neighbors. Its brightness comes mostly from how near it is to us, not from any extraordinary size. In actual physical scale, Sirius A measures only about 1 7/10 times wider than our Sunday A modest jump. Barely a hop into the world of giants. This was the first great lesson about stars. Brightness lies. A flashlight held close looks brighter than a stadium spotlight a mile away. The night sky plays the same trick on us, and Sirius was the master illusionist that fooled astronomers for centuries. Then came an even stranger discovery. Sirius is not alone. In the 1840s, astronomer Friedrich Bessel noticed Sirius wobbling slightly as it moved through space. Something invisible was tugging on it. He predicted a hidden companion, though he could not see it. Years later, telescopes finally caught a faint glimmer beside the bright star. They named it Sirius B. Sirius B turned out to be a corpse, the burnt-out core of a once mighty star, now compressed into something the size of Earth, but holding nearly the mass of our Sunday. A teaspoon of its material would weigh several tons on Earth. Astronomers call this kind of object a white dwarf, and Sirius B was the first one ever confirmed. Think about what that means. Long ago, billions of years before humans existed, Sirius B was likely the larger and more dramatic of the pair. It burned through its fuel faster, swelled, shed its outer layers, and collapsed. What remains is a glowing ember about the size of our planet. Sirius A, the bright one we see today, will eventually follow the same path. So will our Sunday. So will most stars in the universe. They live, they burn, they die, and they leave behind these strange, dense corpses scattered through the dark. But the stars we are chasing in this journey do not end as quiet white dwarfs. They are too big, too hungry, too violent. Their deaths shake galaxies. Sirius taught astronomers something important. To find the true giants of the universe, you cannot trust your eyes. Brightness deceives. Distance disguises. The real monsters often hide farther away, dimmer to our view, but bigger than anything close by could dream of being. So, astronomers started looking deeper. They began hunting for stars whose light traveled hundreds, then thousands of light years before reaching us. Stars that looked unremarkable through a telescope, but, when measured properly, turned out to be larger than entire planetary orbits. The first true giant they uncovered burned with a blue fire so intense it would scorch any world unfortunate enough to drift near it. That hunter's prize was a star most people have heard of but few understand. Look up at Orion, the hunter, on a winter evening. Most people stare at his 3 belt stars first, then their eyes drift to his shoulder, where Betelgeuse glows red. But the star that should steal your attention sits at his foot, Rigel, a point of cold blue-white light, sharp as a chip of diamond. It looks delicate from Earth, almost dainty. The reality is anything but. Rigel sits roughly 860 light-years away from us. The light entering your eyes tonight left that star around the time medieval knights were riding through Europe. And despite that immense distance, Rigel still ranks as one of the brightest stars in our entire night sky. A star that bright, that far away, has to be a beast. Rigel measures about 78 times wider than our Sunday. If you swapped our sun for Rigel right now, the inner planets would be incinerated instantly. Mercury, Venus, and Earth would be inside the star. Our entire daytime sky would be blue fire. Now hold on, because the size is only the appetizer. Rigel pumps out about 120,000 times more energy than our sun every single second. Standing anywhere near it would not be a vacation. It would be vaporization before you finished blinking. That blue color tells the whole story. In the world of stars, color is temperature. Red stars are cooler, burning around 3,000 degrees on their surface. Yellow stars like our sun sit around 10,000 degrees Fahrenheit. White stars run hotter still, but blue stars, the rare elite, burn at 20,000 degrees Fahrenheit and beyond. Rigel is one of those blue beasts, a blue supergiant. These blue giants burn through their fuel at a terrifying pace. While our sun has happily burned for 4.5 billion years and has another 5 billion ahead of it, Rigel is already in trouble. It is only about 8 million years old, and astronomers believe it will explode within the next few million years, a heartbeat in cosmic time. When Rigel goes, it will not fade gently. It will detonate as a supernova, so brilliant that it will outshine every star in the night sky combined. People on Earth, if humans still exist by then, will see a second sun appear at night. It will be visible during the day. The explosion will glow for weeks, maybe months, before slowly fading into a strange new emptiness in the constellation of Orion. Rigel also hides a secret. It is not actually one star. It is at least 3, possibly 4, locked in a gravitational dance. The main star, the giant we see, is orbited by smaller companions that themselves dwarf our Sunday. From a planet circling that system, the sky would never go dark. There would always be a brilliant blue daylight on at least one side. Astronomers consider Rigel a teenager among supergiants. Powerful, beautiful, but ultimately small compared to what comes deeper into the cosmic wilderness. There are stars that make Rigel look like a candle. The blue beasts burn fast and bright. The red ones, however, swell to sizes that defy belief, and one of them sits closer than you might think, currently flickering in ways that have astronomers nervous. Turn back to Orion. Look at his shoulder. That deep orange-red ember is Betelgeuse, and it has been making astronomers anxious for years. Betelgeuse is a red supergiant about 640 light-years away from Earth. That distance matters, because what we see right now is not the Betelgeuse of today. It is the Betelgeuse of around the year 1385. Whatever is happening to that star at this very moment will not reach our eyes for more than 6 centuries. It might already be dead, and we just do not know it yet. The numbers behind Betelgeuse are staggering. The star measures about 764 times wider than our Sunday. Drop it into our solar system, and it would swallow Mercury, Venus, Earth, Mars, and the entire asteroid belt. Its outer atmosphere would brush against Jupiter's orbit. Our planet would not just burn, it would be inside the star. Betelgeuse is not a stable celestial object. It pulses. Its surface boils and churns with massive convection cells, each one bigger than the orbit of Mars. Imagine a single bubble of superheated gas rising from the star's depths, larger than all the inner planets combined, then sinking back down so the next one can rise. The whole star breathes like a living thing. In late 2019 and early 2020, something unusual happened. Betelgeuse dimmed significantly. The brightness dropped by more than half over a few months. People began wondering openly whether the star was about to explode. Astronomers raced to figure out what was going on. The answer turned out to be strange but not catastrophic. Betelgeuse had ejected an enormous cloud of dust from its surface. The cloud blocked some of the light reaching Earth, like a smudge on a window. As the dust drifted away, the star's brightness slowly returned. Still, the dimming was a warning. Stars this big do not behave nicely as they approach death. They convulse. They throw off massive amounts of material. They flicker. Betelgeuse is going to explode. That part is certain. It will detonate as a supernova at some point in the next 100,000 years, possibly tonight, possibly tomorrow, possibly 50,000 years from now. Compared to the lifespans of stars, that range is a thin sliver. When it does go, the show will be unforgettable. Betelgeuse will become brighter than the full moon. People will see it during the day. At night, it will cast shadows. It will dominate the sky for weeks, maybe months, before fading. Eventually, the bright shoulder of Orion will simply be gone, leaving the constellation forever altered. Earth itself will be safe. The star sits too far away to harm us. But the explosion will give scientists their first good look at a supernova up close in modern times. And it could rewrite textbooks overnight. Here is the haunting part. Because the light takes 640 years to reach us, the explosion may have already happened. The signal might be racing across space toward us right now, traveling at the speed of light, due to arrive any night. The star you see in Orion's shoulder might be a ghost. A bigger and stranger giant waits next, one whose heart has already devoured worlds. Drag your eyes south toward the constellation Scorpius, low in the summer sky. There, glowing with a deep blood-red color, sits Antares. The name itself means rival of Mars, because ancient skywatchers thought it looked like an angry red planet that refused to move. It is no planet. Antares is a red supergiant, and it is a monster. Antares lies about 550 light-years from Earth. Its diameter stretches roughly 700 times that of our Sunday. If we placed Antares where our Sun currently sits, the star's outer edge would extend past Mars and reach almost to Jupiter. Earth would be deep inside, vaporized in a flash. The asteroid belt would be ash. Every inner world would be erased before the news even reached the outer planets. To picture this, imagine standing at one end of a football stadium and trying to throw a baseball across to the other end. Now, imagine the baseball is our Sun, and the entire stadium is Antares. That is the kind of scale we are dealing with. Antares burns at a much cooler temperature than blue giants like ridddle. Its surface sits around 6,000 degrees Fahrenheit, which by stellar standards is almost gentle. That coolness is exactly why the star looks so red. Cool stars glow red, hot stars glow blue. Antares is the universe's slow-burning ember, vast but not searing. Despite the cooler surface, Antares pumps out nearly 70,000 times the energy of our Sunday. The reason is sheer size. Even at a lower temperature, a star with that much surface area radiates absurd amounts of light into space. The star has a companion too. A smaller blue star called Antares B orbits the giant at a distance comparable to how far Pluto sits from our Sunday. From a planet near that system, the sky would have one massive red sun dominating half the view, with a smaller blue point of fire moving slowly nearby. The shadows on such a world would be tinged purple. Antares is dying. Like all red supergiants, it has burned through most of its hydrogen and is now fusing heavier and heavier elements in its core. It is currently cooking carbon, oxygen, neon, and other elements in shells around its center. Each new fuel buys the star less time. The carbon stage might last 1,000 years. The neon stage might last a year. The final stages take days, hours. When Antares finally explodes, it will be one of the most spectacular events in our region of the galaxy. The supernova will briefly outshine the full moon. The constellation of Scorpius will lose its brightest jewel forever. In its place, a slowly expanding cloud of debris will spread outward at thousands of miles per second, eventually fading into a dim nebula that future astronomers, if any are still watching, will study for clues about how stars die. Antares is also losing material right now. The star is so loosely held together by gravity that pieces of its outer atmosphere keep peeling away into space, forming a faint glowing shell around it. Future telescopes might one day map this slow leak in detail. For all its size and power, Antares is not the largest red supergiant, not even close. There are stars that make this rival of Mars look like a small candle. But before we visit those, we need to understand how anyone manages to measure these monsters in the first place. Here is a fair question to ask. How can anyone possibly know how big a star is when it sits hundreds or thousands of light years away from us, appearing as nothing more than a single point of light through even the most powerful telescopes? The answer is one of the cleverest tricks in all of science. Astronomers cannot fly out to a star with a measuring tape. They cannot photograph its surface in detail. To human eyes, and to most telescopes, a giant red supergiant 500 light-years away looks identical to a small white dwarf much closer. Just a dot, a pinprick of light. So scientists invented a method that uses physics itself as the ruler. The first step is figuring out how far away a star actually is. astronomers use a technique called parallax. As Earth orbits the Sun, our position in space shifts by about 186 million miles between summer and winter. When you observe a nearby star from those two opposite positions, it appears to move slightly against the much more distant background stars. The closer the star, the bigger the apparent shift. The farther the star, the smaller the shift. By measuring this tiny angle and using basic geometry, astronomers can calculate the exact distance to the star. It works the same way your eyes judge depth. Cover one eye, then switch. Nearby objects jump. Faraway objects barely move. Once the distance is locked in, the next step is brightness. Telescopes measure how much light from the star actually reaches Earth. This is called apparent brightness. Then, knowing the distance, scientists calculate what the star's true brightness must be at its actual location. This true output is called luminosity. Now comes the temperature. The color of a star reveals how hot its surface is. Red means cool, yellow means medium, blue means searing hot. Astronomers measure the precise color spectrum of a star using instruments called spectrographs, which split starlight into a rainbow and reveal exact temperatures. With luminosity and temperature in hand, physics provides the final piece. There is a law called the Stefan-Boltzmann law that connects how much energy a glowing object emits to its size and temperature. If you know how much light a star pumps out and how hot its surface is, you can solve for its size. A blue star and a red star can shine equally bright in total energy, but only because the red one is enormously larger. The cool surface compensates by being huge. That math reveals the truth. For the very biggest stars, astronomers use additional tools. They watch eclipses where one star passes in front of another, measuring how long the dimming takes. The longer the eclipse, the bigger the star. They use interferometry, linking multiple telescopes together to act as one giant lens, occasionally resolving the disk of a nearby supergiant well enough to measure it directly. Even with all these tools, error bars remain wide for the biggest stars. A hypergiant might be measured at 1,500 solar radii one year and 2,000 the next, depending on which method was used and what the star was doing at the time. These monsters pulse and shed material constantly. Their edges are fuzzy. That uncertainty is why the title of biggest known star keeps changing. New measurements topple old champions every few years. Every time astronomers refine their tools, the leaderboard shuffles. The next contender holds a strange name and an even stranger color. In the constellation Cepheus, hidden deep in the northern sky, sits a star so red that the great astronomer William Herschel nicknamed it the Garnet Star, back in the 1700s. Through a small telescope, it does not look white. It does not look orange. It looks like a glowing ember of pure ruby, a single drop of red wine suspended in the dark. Its formal name is Mu Cephei. It is one of the most beautifully colored stars visible from Earth. Mu Cephei is a red supergiant about 2,500 light-years away from us. Its light has been traveling toward Earth since roughly the time the ancient Greeks were inventing democracy. And it is enormous. Estimates of its size vary, but it is roughly 1,400 times wider than our Sunday. Drop Mu Cephei into our solar system and it would swallow everything out to the orbit of Saturn. Earth, gone. Mars, gone. Jupiter, gone. The asteroid belt, vaporized. The gas giants, consumed. Only the icy outer reaches of the solar system would survive, and even those would be roasted by the heat radiating outward from this monstrous ember. The reason Mu Cephei looks so deeply red comes from its low surface temperature, around 6,300 degrees Fahrenheit. That sounds hot, but for a star, it is downright cold. Cooler temperatures mean longer wavelengths of light, which means the star's glow shifts toward the deepest end of the red spectrum. The result is that ruby color that captivated Herschel and still captivates astronomers today. Mu Cephei pulses. It does not just sit there glowing steadily. The star expands and contracts in irregular cycles that can take anywhere from 2 years to 12 years to complete. Its brightness changes noticeably over that time. Astronomers call this kind of star a semi-regular variable. The pulses are caused by instabilities deep inside the star, where competing layers of fusion and convection battle for control. Picture a balloon being inflated and deflated by an unsteady hand. The balloon swells, the air pushes back, the hand pulls more out. Now make that balloon a star 1,400 times bigger than our Sunday. The energy involved in each pulse is more than our Sun will release across its entire 10 billion year lifetime. Mu Cephei also leaks. Its outer atmosphere is so loosely bound by gravity that the star is constantly throwing material into space. Streams of glowing gas drift away, forming a faint shroud that stretches for light years around the giant. From far enough away, the star would look like a dim red lantern wrapped in a luminous fog of its own breath. This star has another distinction. It is one of the most luminous red supergiants known. Mu Cephei emits about 350,000 times the light of our Sunday. Most of that light, however, is in the infrared part of the spectrum, which human eyes cannot see. If our eyes could perceive infrared, Mu Cephei would dominate a section of the night sky, like a small fire. Astronomers expect Mu Cephei to explode as a supernova within the next few 100,000 years. When it does, the Garnet star will become a brief but stunning beacon in the northern sky, possibly visible during daylight hours. The next star on our journey hides something nearly impossible. A second star buried inside its own outer atmosphere. Some stars are so large that they break what we think of as normal celestial mechanics. Stars are supposed to orbit each other from a distance, like skaters circling on a frozen lake. They are not supposed to touch. They are not supposed to overlap. VV Cephei A did not get that memo. This star sits about 5,000 light-years from Earth, in the same constellation as the Garnet star. It is a red hypergiant, one rank above supergiant, and its dimensions are difficult to grasp. VV Cephei A measures somewhere between 1,000 and 1,600 times wider than our Sunday. The exact number bounces around because the star is so chaotic that it changes size depending on where in its pulse cycle it sits. If VV Cephei A replaced our Sun, its outer atmosphere would extend past Saturn. Most of our solar system would be inside the star. Now here is where things become genuinely strange. VV Cephei A has a companion. A second star called VV Cephei B, which is itself massive, roughly 10 times wider than our Sun and burning blue hot. Under normal circumstances, these two stars would orbit each other at a respectful distance. But VV Cephei A is so absurdly enormous that VV Cephei B actually skims through the outer layers of the bigger star during part of its orbit. Imagine a planet trying to orbit our Sun, but the planet's path takes it briefly inside the Sun's outer atmosphere every 20 years before swinging back out. That is essentially what is happening at VV Cephei. The smaller star plows through the giant's puffed-up gaseous envelope on every pass, then emerges back into open space. The result is spectacular and chaotic. When VV Cephei B punches through the outer layers of VV Cephei A, it stirs up massive amounts of material. Vast streams of gas get pulled away. Shock waves ripple through the bigger star. The whole system pulses with bizarre brightness changes that astronomers track carefully. The orbital period is about 20 Earth years. Each time the smaller star makes its plunge, the entire VV Cephei system goes through observable changes that take months or years to settle back down. Nothing about this setup is stable in the long term. Eventually, the gravitational chaos and constant material exchange will rip the system apart or merge the two stars into a single, even more violent object. VV Cephei A is also losing mass rapidly. The star throws roughly 1 Earth's worth of material into space every few years, more during certain phases. Over millions of years, it will shed enough matter to dramatically change its character. What makes VV Cephei a particularly eerie is how loosely it holds itself together. Its average density is so low that if you scooped up a chunk of its outer atmosphere, you would find it thinner than the air inside a vacuum chamber on Earth. The star is enormous, yet its outer regions are barely there. Most of the mass is concentrated deep in the core. Light from this star's surface takes almost 9 hours to travel from one side to the other. Our sun's light makes the same journey in about 2 seconds. The next star up the leaderboard pushed astronomers to the very edge of what their equations could explain. For a while, it sat at the top, considered by many to be the largest known. Deep in the constellation Cygnus, the swan that flies along the Milky Way, there sits a star most people have never heard of, Ky Cygni. It does not have ancient mythology attached to it. It does not appear in poetry or folklore. It is too dim from Earth to catch the naked eye. Yet for a brief period, Ky Cygni held a claim to being one of the largest stars ever measured. Ky Cygni sits about 5,000 light-years away from us. The light-reaching telescopes today began its journey when the Egyptian pyramids were being built. The star is buried in dust, hidden from our view, which is part of why it is so dim despite its massive output. Early measurements put Ky Cygni at an absolutely staggering size. Some estimates pushed it to nearly 2,850 solar radii, which would have made it one of the biggest stars ever discovered. Drop a star that size into our solar system and its surface would extend well past the orbit of Neptune. The entire familiar planetary realm would be inside the star. Here is the catch. That 2,800 figure broke the models. Stellar physics has rules. Stars cannot grow infinitely large. Above a certain size, a star's outer layers simply cannot hold themselves up against the radiation pressure pushing outward from the core. The material gets blasted away into space, faster than gravity can pull it back. Theoretical limits suggest that even the biggest possible red hypergiants should max out somewhere around 1,500 to 2,000 solar radii. Ky Cygni at 2,800 should not exist. So, astronomers went back to the data. They remeasured. They reconsidered the dust between us and the star, which can affect brightness readings in tricky ways. They looked at multiple wavelengths, refined their distance estimates, and ran new calculations. The newer figures came back lower. Modern estimates put Ky Cygni closer to about 1,030 solar radii, possibly up to 1,400. Still huge, still a monster, but no longer a record breaker, no longer a paradox that defied physics. Even at the smaller, revised size, Ky Cygni would swallow our entire solar system out to past Jupiter. Its outer atmosphere would brush against Saturn. The star pumps out roughly 270,000 times the energy of our sun, most of it as infrared light invisible to human eyes. The story of Ky Cygni reveals something important about this hunt for the biggest star. The leaderboard is messy. Measurements depend on dust, distance, brightness assumptions, and which model of stellar physics you use. A star that looks like a champion one year might be downgraded the next when somebody rechecks the math. Ky Cygni is also a star that has been losing mass aggressively for a long time. It is wrapped in a thick shroud of its own ejected material, a dusty cocoon that astronomers struggle to see through. Some scientists believe the star is in the final stages of its life, possibly only tens of thousands of years away from going supernova. When it does explode, the surrounding dust will light up dramatically, creating one of the most photogenic supernova remnants the galaxy has ever produced. The next stop on our journey takes us to a star that hides at the edge of our own galaxy, a quiet giant most people have never seen. Far out toward the edge of our Milky Way galaxy, in a region most amateur stargazers never bother with, sits a star called V354 Cephei. It does not have a memorable name. It does not anchor a famous constellation. It hides in plain sight, glowing dimly from a distance of about 9,000 light-years. Yet V354 Cephei is one of the most extreme red hypergiants ever catalogued. The star measures somewhere between 600 and 890 solar radii, depending on which measurement you trust. At its largest estimates, V354 Cephei would extend past the orbit of Jupiter if placed where our Sun is. Earth, Mars, the asteroid belt, and Jupiter itself would all be roasting inside its outer atmosphere. What makes V354 Cephei especially interesting is its location. The star sits on the outer fringes of our galaxy, far from the crowded core where most massive stars are born. Out there, in the thin stellar suburbs, you do not expect to find monsters this size. Hypergiants typically form in dense star-forming regions where massive clouds of gas can collapse into enormous stellar babies. The galactic edge is sparse, cold, quiet. So how did V354 Cephei get so big out there? Astronomers have a few theories. One possibility is that the star drifted outward over millions of years, born somewhere closer to the galactic center, but eventually wandering to its current position. Another theory suggests that V354 Cephei is part of a small cluster of massive stars that form together in an unusual gas cloud out in the galactic suburbs. The cluster has since dispersed, leaving the giant as a lonely survivor. Either way, V354 Cephei breaks the usual rules about where you find stars this big. The star is currently in the late stages of its life. It has burned through most of its hydrogen fuel and is now fusing heavier elements in its core. Each new fuel source releases less energy than the last, which means the star's life is winding down rapidly. In stellar terms, V354 Cephei is an old man with months left to live, except those months are measured in tens of thousands of years. Like other red hypergiants, V354 Cephei pulses. Its diameter changes by significant amounts over cycles that take years to complete. During an expansion phase, the star can grow noticeably bigger before contracting back. These pulses are violent. They throw enormous amounts of material off the star's surface and into space, where it forms a glowing shroud of dust and gas around the giant. The material being shed by V354 Cephei is not lost forever. It will eventually mix with the surrounding interstellar medium, providing the raw materials for future stars and planets. The carbon and oxygen and other heavy elements being forged in this giant's core right now might one day end up in the bones of creatures on a planet that does not exist yet, orbiting a star that has not yet been born. When V354 Cephei finally explodes as a supernova, the event will briefly outshine all the other stars in that quiet section of the galaxy. The shockwave from the explosion will spread outward through space, compressing nearby gas clouds and possibly triggering the formation of new stars in the wake of the old one's death. A red giant lives, dies, and seeds the next generation. The next star on our list does this on a scale that approaches the impossible. About 12,000 light-years from Earth, in the constellation Ara, lies one of the most extreme star clusters in the entire Milky Way galaxy. It is called Westerland 1, and it is a stellar nursery on steroids. Inside this cluster, dozens of massive stars are crammed into a tiny pocket of space, all blazing with monstrous energy and ripping at each other gravitationally. The undisputed king of Westerland 1 is a star simply called Westerland 1 to 26. This star is a red supergiant, possibly verging on hypergiant status, with a size estimate that pushes between 2,000 and 2,500 solar radii. If correct, that places Westerland 1 to 26 firmly among the largest stars ever measured. Drop it into our solar system, and its outer edge would extend past the orbit of Saturn, possibly out toward Uranus. Here is where things become physically uncomfortable. The Eddington limit is a theoretical boundary in physics that says stars cannot grow beyond a certain size before their outer layers literally get blown off by the radiation pressure from the core. Above that limit, the star tears itself apart. Westerland 1 to 26 sits dangerously close to that line, possibly even crossing it. How does the star hold itself together? Astronomers are not entirely sure. Some believe that strong magnetic fields wrap around the giant like an invisible web, helping to contain the outward pressure. Others suspect the star is, in fact, slowly losing material at a rate fast enough to keep it from completely exploding right now, a kind of slow-motion disintegration that buys it tens of thousands of years before the inevitable end. Westerland 1-26 has another bizarre feature. It is surrounded by a shell of radio-emitting material that astronomers can detect using radio telescopes. The shell is huge, stretching for trillions of miles around the star. It is made of gas that the giant has thrown off over the past several thousand years. The radio signal coming from the shell is so strong that it ranks among the brightest natural radio sources in our part of the galaxy. The cluster around Westerland 1-26 is itself a marvel. Within a region of space, only a few light years across, more than 200 massive stars are crammed together. Many of these stars are dozens of times the mass of our Sun. The gravitational interactions inside the cluster are intense. Stars regularly swing close to each other, sometimes exchanging material, sometimes ejecting smaller stars out of the cluster entirely at high speeds. If a planet existed in Westerland 1, the night sky would be unlike anything we can imagine. Dozens of brilliant stars would dominate the view, each one bright enough to read by. There would be no true darkness. The combined light from all those giants would keep the sky lit even on the deepest night, with shifting colors as different stars rose and set. Westerland 1-26 is also young. Despite its massive size and advanced evolutionary state, the entire cluster is only about 4 to 5 million years old. In stellar terms, that is still a baby. The fact that Westerland 1-26 has already aged into a red supergiant in such a short time tells us how fast these monster stars burn through their fuel. The star will not last much longer. Within the next few 100,000 years, it will explode in a supernova of incredible power. The blast will tear through the rest of the cluster, scattering material across thousands of light years. But the next stop takes us beyond our galaxy entirely. We have been touring the Milky Way so far, hopping from one monster star to the next within our own galactic neighborhood. Now we leave home. About 160,000 light-years from Earth sits the large Magellanic Cloud, a smaller galaxy that orbits our Milky Way like a faithful companion. It can be seen with the naked eye from the southern hemisphere as a faint smudge in the night sky. Inside that distant galaxy lurks one of the most extreme stars ever discovered. It is called Wo-G64. The name sounds like a serial number, because it is. Wo stands for the catalogue where the star was first listed, and G64 is its entry number. The star itself is anything but ordinary. Wo-G64 is a red hypergiant with a diameter estimated at around 1,540 solar radii. If placed in our solar system, its outer atmosphere would stretch beyond the orbit of Saturn. What makes Wo-G64 truly bizarre is what surrounds it. The star is wrapped in a thick, dense torus of dust, a donut-shaped cloud of material that the star itself has been throwing off for hundreds of thousands of years. The torus is so thick that it actually obscures most of the star's light from our perspective. Looking at Wo-G64 directly is like trying to see a light bulb through a wool blanket. That dust torus is no small structure. It stretches for about 120 trillion miles around the star and contains material equivalent to several times the mass of our Sun. Astronomers have used powerful infrared telescopes to peer through the dust and study the giant inside, and what they have seen is a star in serious trouble. Wo-G64 is shedding mass at one of the highest rates ever recorded for a single star. Every 10,000 years or so, the giant loses material equal to the entire mass of our Sun. That gas and dust gets flung outward into space, forming the surrounding torus and feeding the cocoon that hides the star from view. This kind of mass loss is so extreme that astronomers struggle to model it. Where does all that energy come from? How does the star keep blasting material away without simply blowing itself apart? The answers are not fully understood. Wo-G64 is essentially eating itself from the outside in, slowly stripping away its own atmosphere while continuing to fuse heavier elements at its core. The temperature of voyager 64 is around 5,400 degrees Fahrenheit, on the cooler end even for red hypergiants. Despite that, the star's massive surface area means it pumps out roughly 280,000 times the energy of our Sunday. Most of that radiation, of course, gets absorbed by the surrounding dust torus, which then re-emits the energy as infrared light. Whoa, G64 also shows signs of a possible companion. Some observations suggest a smaller star may be orbiting inside or near the dust torus, gravitationally stirring the material and contributing to the chaotic mass loss. If true, this would be similar to the bizarre setup at vanish, where a smaller star helps disrupt a giant's outer layers. The end of voyager 64 will be violent. When the star finally collapses and explodes, the supernova will light up the large Magellanic Cloud in a way visible to the naked eye from Earth. The expanding shockwave will plow into the surrounding dust torus, creating one of the most spectacular supernova remnants ever observed. But as strange as voyager 64 is, the next star plays an even weirder game with its own size. In the constellation Cepheus, only a few degrees away from the Garnet Star, sits another red giant with a peculiar habit. Its name is RW Cephei. It does not just pulse, it changes shape. RW Cephei lies about 3,500 light-years from Earth. The star is classified as a yellow hypergiant, though its color shifts unpredictably, and it sometimes behaves more like a red supergiant. That confusion is the first hint that RW Cephei is not a normal star. It does not stay still long enough for astronomers to fully pin it down. Estimates place its size somewhere around 900 to 1,600 solar radii. The wide range exists because the star physically swells and shrinks in ways that defy easy measurement. Sometimes it appears smaller, sometimes much larger. The same star, observed 5 years apart, can give wildly different size readings. What is happening inside RW Cephei? The star is in a transitional phase of its life. It has burned through most of its hydrogen and is now in the unstable territory where massive stars decide their final fate. Some massive stars at this stage become Wolf-Rayet stars, peeling off their outer layers to expose the searing hot core beneath. Others bloat into red supergiants and stay there until they explode. RW Cephei seems caught between these options, oscillating between states like a stove burner that cannot decide whether to be on or off. When the star expands, its surface cools and reddens. When it contracts, the surface warms and shifts toward yellow. These changes happen over years and decades, slow enough that any single human observation captures only a snapshot of one phase. RW Cephei also has a strange asymmetry. Recent observations using high-powered telescopes suggest that the star is not perfectly spherical. It has bulges and dimples on its surface, regions where huge convection cells push material outward, and other regions where cooler gas sinks back down. From a hypothetical nearby vantage point, the star would look lumpy, like a glowing apple that was beginning to wrinkle. This asymmetry has practical consequences. The star throws off material in bursts rather than steadily. Some directions get blasted with stellar wind, while other directions remain relatively quiet. The result is an irregular cloud of ejected gas and dust around the star, lopsided rather than evenly distributed. In recent years, RW Cephei made headlines when it dimmed significantly, similar to what Betelgeuse did in 2019. The dimming was caused by a major dust ejection event. The star coughed up an enormous cloud of material that briefly blocked some of its own light from reaching Earth. As the cloud dispersed, the brightness recovered. These dimming episodes are warnings. Stars in the late stages of their lives undergo increasingly violent convulsions before they finally explode. Each ejection peels off another layer. Each pulse stirs the core a little more. Eventually, the balance breaks completely. RW Cephei is a rare laboratory. Stars in this transitional state do not last long, evolutionarily speaking. The phase between supergiant and Wolf-Rayet might last only a few thousand years, a narrow window that astronomers are eager to study while it remains open. Every observation of RW Cephei adds to our understanding of how the most massive stars in the universe end their lives. The next star takes mass loss to a frightening extreme, with consequences that ripple across thousands of trillions of miles. Buried deep in the constellation Cygnus, hidden behind layers of interstellar dust, sits a star that almost no one has ever seen. To the naked eye, it is invisible. Even through powerful telescopes, it appears only as a dim, fuzzy red point. Yet this hidden giant ranks among the largest stars ever measured. Its name is NML Cygni. NML Cygni sits about 5,300 light-years from Earth. The star measures somewhere between 1,100 and 1,600 solar radii. At its largest estimates, NML Cygni would extend out past the orbit of Jupiter if placed in our solar system. The asteroid belt, the inner planets, all of it would be deep inside the star. The reason NML Cygni is so dim from Earth, despite its massive size, comes down to dust. The star is wrapped in an enormous shell of its own ejected material, much of which has cooled and condensed into solid grains of silicate dust and ice. This dust shell stretches for trillions of miles around the giant, soaking up almost all of the visible light the star emits and trapping it in a dense fog. The dust around NML Cygni does not just sit there, it glows brightly in infrared wavelengths as it absorbs and re-emits the star's energy. Through infrared telescopes, NML Cygni and its surrounding nebula light up like a beacon. To human eyes, it remains nearly invisible. Astronomers describe it as the silent giant, a star hiding in plain sight, missed by anyone who only looks at the sky in visible light. NML Cygni is losing mass at a furious rate, throwing off the equivalent of an Earth-sized chunk of matter every few months. This continuous outpouring is what feeds the dust shell. Over the past 100,000 years, NML Cygni has shed enough material to build a small star of its own out of the discarded remnants. Where does all that energy come from? It comes from the star's own struggle against gravity. NML Cygni is so massive and so swollen that its outer atmosphere is barely held in place. Radiation pressure from the core constantly pushes outward, while convection cells the size of planetary orbits churn material from the depths to the surface and back. The combination creates a turbulent, leaking giant that cannot stop bleeding. The star sits inside a region of space called the Cygnus OB2 Association, a stellar neighborhood packed with massive young stars. NML Cygni is one of the oldest residents of this region, a giant that has aged faster than its companions due to its enormous size. While other stars in Cygnus OB2 are still burning hydrogen happily, NML Cygni has already moved on to fusing heavier elements and is well into the late stages of its life. NML Cygni also pulses. Its brightness changes slowly over cycles of about 1,000 days, with smaller variations on top of the longer pattern. Each pulse causes another round of mass ejection, adding to the dust shell that surrounds the star. Astronomers can track these pulses by watching how the infrared brightness rises and falls. When NML Cygni finally explodes, the supernova will be muffled at first by the surrounding dust shell. The blast will plow into the shell and light it up from the inside, creating a glowing bubble that expands outward across centuries. The remnant left behind will be a gorgeous structure of luminous gas and shock-heated dust. The next star takes the leak even further, becoming almost a fountain in space. In the constellation Sagittarius, near the bright heart of our galaxy, lurks a star that is slowly disassembling itself. VX Sagittarii is a red hypergiant about 1,520 light-years from Earth, and it is in trouble. VX Sagittarii measures around 1,520 solar radii at its peak size, though, like its hypergiant cousins, the star pulses and the exact size varies. Drop VX Sagittarii into our solar system and its surface would brush against the orbit of Saturn. The familiar planets would be nothing more than ash inside a cosmic bonfire. What makes VX Sagittarii particularly noteworthy is the speed at which it is bleeding into space. The star loses mass at a rate of roughly 1 Earth's worth of material every couple of months. Over a decade, it sheds many Earth masses. Over a millennium, enough matter to build small worlds. The star is, in a real sense, evaporating. Though evaporating is the wrong word for something so violent, it is more like a leaking dam, with material gushing out in every direction. This mass loss creates a thick, glowing envelope around the star. Telescopes can resolve this envelope as a fuzzy halo, hundreds of times wider than the star itself. The halo glows in infrared and radio wavelengths because it is full of cooled gas and dust that has been ejected from the giant. The star pulses irregularly, with brightness changes that take a couple of years to complete each cycle. During the bright phases, VX Sagittarii becomes visible to the naked eye on dark nights for observers in the southern hemisphere. During the dim phases, it requires a telescope to find. The pulses are tied to deep convection patterns in the star's interior, where superheated material rises from near the core to the surface and back down again. VX Sagittarii is also sitting in a crowded part of the galaxy. Sagittarius points directly toward the center of the Milky Way, where stars are packed densely and gravitational interactions are intense. The star is not at the galactic core itself, but it is closer than many of its hypergiant cousins. That location matters for its fate. When VX Sagittarii eventually explodes, the supernova will affect a region of space that is already busy with stars, gas clouds, and other massive objects. The cosmic leak from VX Sagittarii has another consequence. The material being shed by the star contains heavy elements forged in its core: carbon, oxygen, silicon, iron. These elements are being scattered into the surrounding interstellar medium, where they will mix with hydrogen and helium clouds and eventually become part of the next generation of stars. This is how the universe builds itself up over time. Every massive star that lives and dies adds its own contribution of heavy elements to the cosmic recipe. Without giants like VX Sagittarii, there would be no carbon in the universe to build life, no oxygen for water, no silicon for rocky planets. We are all, quite literally, made of stardust, much of it forged in stars exactly like this one. VX Sagittarii is also a potential test case for understanding how the very biggest stars die. Its ongoing mass loss may strip enough of the outer atmosphere away to reveal the hot core beneath, transforming the star into a Wolf-Rayet object before it finally explodes. Or the star might keep its red hypergiant shroud right up until the end and explode as a classic red supergiant supernova. But the next star held the title of largest known star for many years, and what happened to it changed how astronomers think about stellar limits forever. For decades, one star dominated the leaderboard of cosmic giants. Astronomy textbooks featured it, documentaries showcased it. Anyone curious about the largest stars in the universe heard the same name over and over: VY Canis Majoris. The star sits in the constellation Canis Major, the same constellation that contains Sirius, though VY Canis Majoris lies much farther away, about 3,900 light-years from Earth. The star is a red hypergiant of staggering proportions, with diameter estimates that have ranged widely over the years. In its glory days, VY Canis Majoris was estimated at around 2,000 solar radii. At that size, the star would extend past the orbit of Saturn if placed in our solar system. The entire familiar planetary realm would be inside the star, with only the outer ice giants barely surviving on the fringes. More recent measurements have brought that figure down. Modern estimates put VY Canis Majoris closer to 1,300 to 1,700 solar radii. Still enormous. Still one of the largest stars known, just no longer the absolute champion. Even at the lower estimates, VY Canis Majoris is a beast. The star pumps out around 270,000 times the energy of our Sun, mostly in infrared light. Its outer atmosphere is so loosely bound by gravity that material peels away constantly, forming an extensive nebula of ejected gas and dust around the star. What makes VY Canis Majoris truly fascinating is the violence of its outer winds. The star throws off material in irregular bursts, not in a smooth, steady flow. These bursts create intricate structures in the surrounding nebula, long arcs of glowing gas, knots of dense material, streamers and loops that twist away from the star in complex patterns. Photographs taken by the Hubble Space Telescope have revealed a chaotic, swirling cloud around VY Canis Majoris that looks more like an explosion frozen in time than a steady stellar wind. The cause of these violent ejections may be massive convection cells in the star's interior. Picture the boiling surface of a pot of soup, where bubbles of hot liquid rise from below, break the surface, and sink back down. Now, make each bubble the size of our entire solar system. When one of these convection cells reaches the star's surface and bursts, it can launch a colossal mass of material into space all at once. VY Canis Majoris is also dimming slowly over time. Astronomers have noticed that the star's brightness has been gradually decreasing over the past century. The reason is not the star itself, but the growing dust cloud around it. As more material gets ejected and condenses into dust, less of the star's light makes it through to Earth. We are watching the star slowly disappear behind its own breath. The fate of VY Canis Majoris is a subject of debate. Most stars its size end their lives in supernova explosions, but VY Canis Majoris might be too massive for a normal supernova. Some astronomers think it could collapse directly into a black hole without a major explosion, or produce a hypernova that briefly outshines an entire galaxy. When the end finally comes, the surrounding dust cloud will play a starring role. The supernova shockwave will plow into the nebula, lighting it up from within and creating one of the most spectacular cosmic light shows our galaxy has ever produced. But VY Canis Majoris no longer holds the crown. A new champion claimed the throne, and it did so by a comfortable margin. Far across the galaxy, about 20,000 light-years from Earth, in the constellation Scutum, sits a star cluster called Stephenson 2. Inside that cluster lurks the current heavyweight champion of the known universe, a star whose size pushes against the very limits of what physics says is possible. Its name is Stephenson 2-18, often shortened to Saint 218. Estimates place Stephenson 2-18 at around 2,150 solar radii. That is the most reliable current figure, though some measurements have pushed even higher. At that size, the star would dwarf our entire solar system. If placed where our Sun sits, Stephenson 2-18's outer atmosphere would stretch far past the orbit of Saturn, possibly out toward Uranus. Try to picture that scale. Our Sun is so big that more than 1 million Earths could fit inside it. Stephenson 2-18 is so big that 10 billion of our suns could fit inside it. The numbers spiral into territory that human imagination simply cannot hold. Light takes about 9 hours to travel from one side of Stephenson 2-18 to the other. That is longer than a workday. Light from our own sun makes the same journey in about 2 seconds. The star is a red supergiant, possibly a red hypergiant, depending on which classification you use. Its surface temperature sits around 6,300 degrees Fahrenheit, which is on the cool side for a star but explains its deep red color. Despite that cool surface, Stephenson 2-18 pumps out energy equivalent to about 440,000 times that of our Sun, almost all of it in the infrared range. Stephenson 2-18 sits inside a cluster of about 24 other red supergiants, which is itself a cosmic oddity. Most red supergiants are loners. Finding a whole cluster of them packed together is like finding a herd of elephants in a single backyard. The cluster appears to be a remnant of a massive star-forming event that happened about 20 million years ago, producing dozens of giant stars all at once. Most have already died. Stephenson 2-18 is one of the survivors, and the largest of them all. The star is currently in the late stages of its life. It has burned through most of its hydrogen and is now fusing heavier elements in its core. Each new fuel buys less time than the last. The carbon stage might last a few hundred years. The neon stage, perhaps a year. The final stages take days. When Stephenson 2-18 explodes, the event will be one of the most powerful supernovae ever recorded in our galaxy. Some astronomers believe the star is so massive that it might not produce a normal supernova at all. Instead, it could collapse directly into a black hole, swallowing itself with a brief flash of light and leaving behind a cosmic predator hidden in the dust of scutum. Or it could produce a hypernova, a supernova explosion so powerful that it briefly outshines all the other stars in the Milky Way combined. The blast wave would send shockwaves rippling across thousands of light years, possibly triggering the formation of new stars in distant gas clouds and seeding the surrounding region with the heavy elements forged in the giant's core. The reason Stephenson 2-18 stands out is not just its size. It is how close the star sits to the theoretical maximum that any star can reach. Beyond Stephenson 2-18 lies an invisible wall in physics, a boundary that astronomers call the Eddington limit, and that wall changes everything about how we understand giants. There is a wall in the universe. You cannot see it. You cannot touch it. It does not stop spaceships or block signals, but it stops stars cold. No star has ever been confirmed to grow past it. Astronomers call this wall the Eddington limit, and it explains why even the biggest stars we know of seem to top out around 2,000 solar radii. The man behind the name is Arthur Eddington, an English physicist who worked out the math in the early 1900s. He was studying how stars hold themselves together. The answer, it turns out, is a constant tug-of-war between two forces. Gravity wants to crush a star. Every atom of hydrogen and helium and heavier elements is pulled toward the center of the star by its own immense gravitational field. If gravity won completely, every star would collapse into a tiny point in seconds. The opposing force is radiation pressure. Deep inside a star's core, fusion produces a flood of light and energy that pushes outward. Photons, the particles that carry light, slam against atoms on their way out and shove them away from the center. This outward push balances gravity and keeps the star puffed up to its current size. For most stars, the balance is easy. Gravity slightly wins, and the star stays compact. For our Sun, the balance is steady. The Sun has been holding its shape for nearly 5 billion years and will keep doing so for billions more. For monsters like Stephenson 2-18, the balance is precarious. The star is so massive that the radiation pressure from its core is incredibly powerful, almost strong enough to overcome gravity entirely. The star is right on the edge of blowing itself apart from the inside. The Eddington limit is the precise point where radiation pressure equals gravity. Above that point, the outward push wins, and the star's outer layers get blasted away into space faster than gravity can pull them back. The star cannot grow any larger. It physically cannot. The math says so. For red hypergiants, the limit translates to a maximum diameter somewhere around 1,500 to 2,500 solar radii, depending on the star's mass and chemistry. Stephenson 2-18 sits right at the upper end of that range. It is, essentially, hugging the wall. What happens to a star that tries to grow past the limit? It begins to disintegrate. Its outer layers blow off in massive winds, peeling away from the surface and flying into space at speeds of hundreds of miles per second. The star sheds mass faster and faster, eventually losing so much material that its core is exposed. From there, it may transform into a different kind of star entirely, like a Wolf-Rayet, which is a stripped-down stellar core burning naked in space. This is why finding a star bigger than Stephenson 2-18 is so difficult. The biggest measurements always seem to bump up against the same physical ceiling. Anything that tries to exceed it tears itself apart in a stellar timescale that is short compared to the lifespan of the universe. There is a loophole, however. The Eddington limit assumes a star with normal, present-day chemistry. In the early universe, when the first stars were forming out of pure hydrogen and helium, the rules were different. Those first stars could grow to sizes that would be impossible today. To find truly absurd sizes, we need to look back in time, to a universe that no longer exists. Numbers in astronomy can be slippery. When astronomers say a star is 2,000 solar radii wide, the human brain hears the words but does not really feel the scale. To make it feel real, we need to talk about volume, not just diameter. A star is roughly a sphere. The volume of a sphere grows much faster than its diameter. Double the diameter, and the volume increases 8-fold. Triple the diameter, and the volume increases 27 times. By the time you reach a star with a diameter 2,000 times that of our Sun, the volume difference becomes truly bizarre. How many of our suns could fit inside a star like Stephenson 2-18? Roughly 10 billion. Read that number again, 10 billion. If you could somehow scoop up our sun and start packing copies of it into Stephenson 2-18, you would need 10 billion of them to fill the space. 10 billion glowing yellow stars stuffed into the volume of one red supergiant. To put 10 billion into perspective, that number is bigger than the human population of Earth. There are about 8 billion people alive today. 10 billion suns inside one star is more suns than there are people on this planet. Try a different comparison. If our sun were the size of a basketball, Stephenson 2-18 would be a sphere over half a mile across. Standing at the center, you would not be able to see the surface. The opposite side of the star would be hidden beyond the horizon, just like the curve of the Earth hides distant objects from view. Light, the fastest thing in the universe, takes about 9 hours to cross the diameter of Stephenson 2-18. Imagine standing on the surface of such a star, somehow surviving the heat and radiation. You point a flashlight straight ahead. The beam takes nearly half a day to reach the far side. By the time the light arrives, the star has rotated, the surface has shifted, and the patch you aimed at is no longer there. A jet airplane flying at typical cruising speed would take more than 300 years to go from one side of Stephenson 2-18 to the other. The fastest spacecraft ever built by humans, the Parker Solar Probe, would still need decades to make the crossing. Now think about mass. Stephenson 2-18 is not just bigger than our Sunday. It is also more massive, though the mass difference is much smaller than the size difference. The star contains about 20 to 40 times the mass of our Sunday. The reason the volume is so much larger while the mass is only modestly larger comes down to density. Stephenson 2-18 is incredibly thin. Its outer atmosphere is more diffuse than the air at the top of Mount Everest. If you scooped up a chunk of the star's surface gas, you would find it almost ghostly, a faint shimmer of hydrogen atoms barely held together. The mass is concentrated in the deep core, where temperatures and pressures crush atoms into a dense plasma. This combination of huge volume and modest mass makes hypergiants strange creatures. They are mostly empty space, dressed up as stars. From a distance, they look like solid spheres of glowing gas, but up close, you would find them almost transparent in their outer layers. The deeper you go, the denser the star becomes. By the time you reach the core, the density has multiplied billions of times. That core is where all the action happens, where heavy elements are forged, where the fate of the star is decided. And the fate of stars this big is always the same. A short, brilliant life, followed by an ending so violent it shapes whole galaxies. Most things in the universe last a long time. Galaxies survive for billions of years. Planets persist for billions more. Even our sun, an unremarkable yellow star, will burn for about 10 billion years before reaching the end of its life. Hypergiants do not get that luxury. A red hypergiant, like Stephenson 2-18, lives for only about 10 million years. That sounds like a long time by human standards, but in cosmic terms, it is an eye blink. If the lifespan of the universe were compressed into a single year, a hypergiant would live for less than a second. Why do these monsters die so fast? The answer comes down to fuel consumption. Stars run on nuclear fusion. In the core, hydrogen atoms are smashed together under tremendous pressure and heat, fusing into helium and releasing energy. That energy is what makes stars shine and what holds them up against their own gravity. Bigger stars have more fuel. You might think more fuel means a longer life. The opposite is true. Bigger stars burn their fuel at vastly higher rates because their cores are hotter and more compressed. A hypergiant fuses hydrogen so quickly that it consumes more fuel in 1,000,000 years than our sun will burn in its entire 10 billion year lifetime. The math works out cruelly. A star 10 times more massive than our sun lives only about 30 million years. A star 20 times more massive lives about 10 million years. A star 40 times more massive, like the progenitor of Stephenson 2 to 18, lives only a few million years before exhausting its hydrogen. After hydrogen runs out, the star moves on to fusing heavier elements. First helium, fusing into carbon and oxygen, then carbon, fusing into neon and magnesium, then neon, then oxygen, then silicon. Each new fuel buys the star less time than the last because each fusion process is less efficient and releases less energy per reaction. The helium burning phase might last several 100,000 years. The carbon phase, a few hundred years. The neon phase, less than a year. The oxygen phase, perhaps months. The silicon phase, only days. By the time the star is fusing silicon into iron, the end is hours away. Iron is the death sentence. When fusion produces iron, the process stops releasing energy and starts absorbing it. The core can no longer support itself against gravity. Within a single second, the iron core collapses inward, compressed to densities that exceed those of an atomic nucleus. The collapse triggers a rebound shockwave that races outward through the rest of the star, blasting the outer layers into space at speeds approaching 1/10 the speed of light. That is a supernova. The whole process, from the first iron atoms forming in the core to the explosion tearing the star apart, takes about 1 second. The death of a hypergiant happens in less time than it takes you to blink twice. For all the millions of years a hypergiant spent burning through its fuel, growing to enormous size, dominating its corner of the galaxy, the actual ending is over almost instantly. The star goes from a stable, glowing giant to an exploding fireball in the time it takes a flashbulb to fire. Astronomers can never predict exactly when a specific hypergiant will explode. They can narrow it down to within a few 100,000 years for any given star. But the moment of explosion happens too fast and depends on too many internal variables to forecast precisely. This is what makes hypergiants like Stephenson 2 to 18 so terrifying. We do not know if they will explode tonight, next year, or 50,000 years from now. They sit out there, glowing red in the dark, ticking away the final moments of cosmic timescales. And when the explosion comes, it does not go out quietly. A supernova is the loudest event the universe knows how to make. When a hypergiant's core finally collapses, the outer layers of the star get blasted into space at incredible speeds. The total energy released in a single supernova explosion equals the energy our sun will produce across its entire 10 billion year lifetime. All of that energy comes pouring out in a matter of seconds. For a brief window, usually a few weeks, a supernova outshines the entire galaxy that contains it. A single dying star produces more light than billions of normal stars combined. From across the universe, telescopes can see the explosion as a bright new point of light, sometimes outshining the host galaxy itself. The shockwave from a supernova travels outward at speeds of thousands of miles per second. As it expands, it sweeps up material in the surrounding space, creating a glowing bubble of compressed gas that can stretch for hundreds of light years. These bubbles, called supernova remnants, persist for tens of thousands of years before slowly fading. Inside the explosion, temperatures reach billions of degrees. Pressures exceed anything found anywhere else in the modern universe. The conditions are extreme enough to forge new elements. Elements like gold, platinum, uranium, and many others are created in supernova explosions and scattered into space, where they eventually become part of new stars and planets. Every gold atom in your jewelry was forged in a supernova. Every iron atom in your blood, every drop of mercury, every shred of silver, every piece of lead. These elements did not exist when the universe was young. They were manufactured, atom by atom, in the cores of dying giants, and then blasted out into the cosmos by supernovae. For massive stars like Stephenson 2 to 18, the supernova is even more violent than usual. The star is so heavy that its collapse generates enough gravitational energy to potentially produce a hypernova, a supernova type that is many times more powerful than a standard one. Hypernovae are rare. Maybe one in every 1,000 supernovae qualifies. They occur when an extremely massive star, often spinning rapidly, collapses in a way that produces twin jets of material shooting out from its poles at nearly the speed of light. These jets are so concentrated and energetic that they can be detected from the other side of the universe. A hypernova in our own galaxy, if pointed in our direction, could pose a real threat to Earth. The radiation from the polar jets could strip away the ozone layer and damage the biosphere. Fortunately, no nearby hypergiants are aimed at us, and the geometry of these explosions makes direct hits extremely unlikely. Even a normal supernova at close range would be dangerous. Astronomers estimate that a supernova within about 30 light-years of Earth could cause significant harm to life on our planet. Beyond that distance, the effects fade quickly. Stephenson 2 to 18, 20,000 light-years away, poses no threat at all. Some supernovae leave behind a strange object at their center. The collapsed core of the original star can become a neutron star, a city-sized sphere of pure neutron matter so dense that a teaspoonful would weigh billions of tons on Earth. Neutron stars spin rapidly and emit beams of radiation that we can detect across thousands of light-years. For the very biggest stars, the core does not stop collapsing at the neutron star stage. It continues compressing until it forms something far stranger, a black hole, a point in space where gravity becomes so intense that not even light can escape. But for the very biggest stars in history, the explosion itself behaves in ways that defy normal supernova physics. Most stars die and leave behind a corpse, a white dwarf, a neutron star, a black hole. The body of the star collapses or compresses into some remnant that lingers for billions of years afterward. Some stars die in a way that leaves nothing at all. No core, no black hole, not even a neutron star. The entire star is converted into pure energy and scattered material, vanishing from the universe completely. These rare events are called pair instability supernovae, and they happen only to the most massive stars in existence. A pair instability supernova requires a star with at least 130 times the mass of our Sun, possibly much more. Such stars are incredibly rare in the modern universe because most regions of space lack the conditions to form them. They were more common in the very early universe, when the first stars were made of pure hydrogen and helium with no heavier elements to interfere with their formation. The mechanism behind a pair instability supernova is bizarre. Inside an extremely massive star's core, temperatures climb so high that the photons of light produced by fusion become extraordinarily energetic. These high-energy photons can do something strange. They can spontaneously transform into pairs of particles. Specifically, they convert into one electron and one positron, the antimatter version of an electron. When this happens, the star loses energy. Light that was supporting the star's outer layers against gravity gets converted into matter, removing the radiation pressure that was holding the star up. The core suddenly has less support than it needs, and gravity begins to win. The core starts to collapse. As it collapses, the temperature rises even more. Higher temperatures produce even more pair production, which removes even more radiation pressure, which causes even faster collapse. The process becomes a runaway disaster. Eventually, the temperature and pressure inside the collapsing core get high enough to ignite a sudden burst of explosive fusion. Massive amounts of oxygen, silicon, and other elements fuse all at once, releasing more energy in a few seconds than a normal supernova does in weeks. The energy is so overwhelming that it tears the entire star apart. Every atom of the star gets blasted into space. There is no leftover core, no collapsed remnant. The star simply ceases to exist as a coherent object, leaving behind only an expanding cloud of debris that slowly cools and disperses. Astronomers have detected a few candidate pair instability supernovae in distant galaxies. The most famous example is a supernova called SN 2006 Grays, which was so bright it was visible across hundreds of millions of light years. The host star is believed to have been at least 150 times the mass of our Sun, possibly much more, and it appears to have been completely destroyed in the explosion. If a pair instability supernova happened in our region of space, the effects would be catastrophic. The total energy output would dwarf normal supernovae by a factor of 10 or more. The expanding shockwave would shape star formation across hundreds of light years, compressing nearby gas clouds into new stellar nurseries. These extreme events also seed the universe with unusual amounts of certain heavy elements. Pair instability supernovae produce massive quantities of iron, nickel, and other intermediate elements. The chemical fingerprint of these explosions is detectable in old, metal-poor stars that astronomers have studied in our galaxy's halo. The fact that pair instability supernovae existed at all suggests that the early universe contained stars far larger than anything alive today. The first generation of stars after the Big Bang were probably bigger, hotter, and shorter-lived than any star we can currently observe. Our journey now turns back in time to the era when stars were truly enormous. Hypernovae are the loudest, brightest, most violent explosions the universe has ever produced. They make ordinary supernovae look like fireworks compared to nuclear bombs. When a hypernova fires off, the entire galaxy hosting it briefly becomes a single point of overwhelming light. The defining feature of a hypernova is the speed and energy of its ejected material. A normal supernova throws debris outward at thousands of miles per second. A hypernova throws material outward at speeds approaching 1/10 or even 1/3 the speed of light. That ejected matter is moving so fast that it produces a blast wave capable of sweeping clean a region of space hundreds of light years across. Hypernovae also produce gamma-ray bursts, the most energetic explosions known. A gamma-ray burst is a focused beam of high-energy radiation that shoots out from the poles of the dying star. If the beam happens to be pointed at Earth, our telescopes detect it as a sudden flash of gamma rays lasting anywhere from a few seconds to a few minutes. We have detected gamma-ray bursts from across the universe, some from galaxies more than 10 billion light-years away. The light from those bursts left its source when the universe was less than 4 billion years old. Despite that immense distance, the bursts are still bright enough to register on our instruments, which gives you a sense of how powerful they are. The mechanism behind a hypernova starts with a very massive, rapidly spinning star. As the star's core collapses, the spin causes the collapsing material to flatten into a disk shape. Material falling onto this disk gets channeled toward the spin axis, where it shoots out as twin jets moving at relativistic speeds. These jets punch through the rest of the star like spears through a balloon. They emerge from the poles of the dying giant and continue outward into space, plowing through any gas and dust they encounter. The jets carry enormous amounts of energy, much of it concentrated in the gamma-ray range. If you happen to be in the path of one of these jets, the experience would be brief and bad. The radiation would arrive without warning, flooding everything in its path with high-energy particles. Planets in the path of a hypernova jet within a few hundred light-years would have their atmospheres stripped away, their oceans boiled, and their surfaces sterilized. Fortunately, hypernovae are rare, and the geometry of their jets makes direct hits unlikely. Each jet covers only a small fraction of the sky as seen from the dying star, so only a small percentage of nearby planets would ever face one head-on. Some astronomers believe that ancient hypernovae may have caused mass extinctions on Earth in the distant past. The Ordovician extinction, which happened about 440 million years ago and wiped out a large fraction of marine life, has been proposed as a possible victim of a nearby gamma-ray burst. The evidence is circumstantial, but the timing and pattern of extinction match what a burst would produce. Hypernovae also play a role in seeding the universe with heavy elements. Their extreme conditions allow for the creation of elements that even normal supernovae cannot produce in significant quantities. Some of the rarest, heaviest elements in the periodic table likely come primarily from hypernovae and from the merger of two neutron stars, another extreme cosmic event. The connection between hypernovae and the most massive stars is not perfect. Not every giant star produces a hypernova when it dies. The conditions required are specific. The star must be very massive, rapidly spinning, and have a particular internal structure. Most hypergiants probably die as standard supernovae, with only a fraction producing the truly extreme hypernova events. Still, the existence of hypernovae proves that stars in our universe are capable of extraordinarily violent ends. And in the very early universe, stars existed that were even bigger and more violent than anything alive today. In the first few 100 million years after the Big Bang, the universe was a strange place. There were no galaxies yet, no rocky planets, no heavy elements scattered through the gas. The cosmos was filled mostly with hydrogen and helium, drifting in vast clouds that slowly collapsed under their own gravity to form the first stars. Among those first stars, some grew to sizes that no modern star could reach. Theory predicts the existence of objects called quasi-stars, which would have been larger than anything in the universe today. A quasi-star is a hypothetical type of star that may have existed only in the early universe. The structure is unlike anything we observe now. At its center sits not a normal stellar core fusing hydrogen into helium, but a black hole, a real, working black hole, sitting in the heart of the star and feeding on the surrounding matter. The black hole at a quasi-star's center is what powers the star's enormous luminosity. As gas falls toward the black hole, it heats up to extreme temperatures and releases vast amounts of energy. That energy radiates outward through the star, supporting the gigantic outer envelope against gravity and keeping the whole structure from collapsing. Quasi-stars are estimated to have grown to sizes far beyond anything we see today. Some theoretical models predict that a quasi-star could reach diameters of tens of thousands of solar radii. A single quasi-star might have been hundreds of times the size of even Stephenson 2-18. If you placed a quasi-star where our Sun is, the outer atmosphere would extend far beyond the orbit of Pluto, possibly engulfing the entire Oort cloud that surrounds our solar system. The whole familiar realm of planets and comets would be deep inside the star. From the perspective of someone standing at the edge of a quasi-star, our entire solar system would be just one small region within the star's vast envelope. Quasi-stars did not last long. The black hole at the center grew steadily as it fed on the surrounding gas, and as it grew, it released more and more energy. Eventually, the radiation pressure became so overwhelming that the star's outer layers were blown away, leaving behind a now much larger black hole sitting alone in space. The lifespan of a quasi-star is estimated at only about 7 million years. Within that brief window, the central black hole would grow from perhaps a few times the mass of our Sun to thousands or even tens of thousands of solar masses. By the time the outer envelope was dispersed, the surviving black hole would already be a giant in its own right. Astronomers believe that quasi-stars may have been the origin of the supermassive black holes that sit at the centers of large galaxies today. The black hole at the heart of the Milky Way, called Sagittarius A star, contains about 4 million solar masses of material. Even bigger black holes exist in other galaxies, with masses of billions of suns. How these monsters got so large so quickly has been a long-standing puzzle, and quasi-stars provide a possible answer by starting with 1,000 solar mass seed black hole inside a quasi-star, then letting it grow over billions of years. Scientists can roughly explain the size of supermassive black holes observed in the modern universe. We have never directly observed a quasi-star. They existed only in the early universe, and any survivors would be far away, with their light having traveled for over 13 billion years to reach us. Detecting one is at the edge of what our current telescopes can do. The James Webb Space Telescope, with its ability to peer into the early universe, may eventually find the first evidence of these long-vanished giants. The first generation of stars after the Big Bang were giants of a different kind, and they shaped the universe we see today. Before galaxies formed, before planets existed, before any star we see today was born, the universe went through a strange, dark phase. For about 100 million years after the Big Bang, the cosmos was filled with hydrogen and helium gas, but had no stars at all. The universe was completely dark. Then, slowly, gravity won. Pockets of denser gas collapsed under their own weight, heating up as they shrank, eventually reaching temperatures and pressures high enough to ignite nuclear fusion. The first stars in the universe lit up. These pioneer stars are called population 3 stars, and they were unlike anything we observe today. Modern stars contain trace amounts of heavy elements like carbon, oxygen, iron, and many others. These elements were not present in the early universe. They had not been forged yet. Population 3 stars formed from gas that was almost pure hydrogen and helium, with no contaminating heavier atoms at all. This pristine gas behaved differently from modern interstellar material. Without heavier elements, the gas could not cool as efficiently when it collapsed. It stayed hotter for longer periods, which meant the collapsing clouds had to grow larger before they could finally form stars. The result was that population 3 stars were huge. Estimates suggest the first stars in the universe ranged from about 100 to 1,000 times the mass of our Sun, possibly even larger in some cases. By comparison, the most massive stars alive today rarely exceed about 150 solar masses. The first stars were in a class entirely beyond anything that exists now. These massive population 3 stars burned hot and bright. Their surfaces reached temperatures of 50,000 degrees Fahrenheit or higher, putting them firmly in the blue end of the color spectrum. Their luminosities were millions of times that of our Sunday. They pumped out vast amounts of ultraviolet radiation that flooded the surrounding gas and began to heat and ionize the entire universe. This process is called re-ionization. Before the first stars, the universe was full of neutral hydrogen atoms, each with a single proton and a single electron. The intense ultraviolet light from population 3 stars ripped the electrons off the atoms, splitting hydrogen back into separate protons and electrons. This change made the universe transparent to most types of light and set the stage for the cosmos we observe today. The first stars also lived very short lives. Their immense masses meant they burned through their fuel quickly. Most population 3 stars probably lasted only a few million years before exploding as massive supernovae. Some of the largest, those over about 130 solar masses, may have ended as pair instability supernovae, completely destroying themselves and leaving behind no remnant. The supernovae of population 3 stars seeded the universe with the first heavy elements. Carbon, oxygen, silicon, iron, and a host of others were forged in the cores of these giants and scattered into the surrounding gas when they exploded. Every later generation of stars formed from gas that contained at least some of these enriched elements, gradually building up the chemical complexity we see in the modern universe. Without population 3 stars, there would be no Earth. There would be no rocky planets at all. The carbon in our bodies, the oxygen we breathe, the iron in our blood, the calcium in our bones, all of these elements trace their origins to the first generation of giant stars and the supernovae that destroyed them. Astronomers have never directly observed a population 3 star. They are too distant and too short-lived. Indirect evidence of their existence comes from studying very old, metal-poor stars in the halo of our galaxy, which carry chemical signatures that match what population 3 supernovae would have produced. Could any star, even hypothetically, swallow our entire solar system many times over? Imagine a star so large that our entire solar system, from the Sun out past Pluto and into the Oort cloud, would fit inside it not just once, but hundreds or thousands of times. A star that could hold our familiar planetary realm like a single grain of sand in a vast desert. Does such a star exist? In the modern universe, no. The Eddington limit and other physical constraints prevent stars from growing that large under current conditions. The biggest known stars, like Stephenson 2 to 18, top out at sizes that would extend roughly to the orbit of Saturn or just beyond. They are huge, but they cannot fit our entire solar system inside them. In the early universe, however, the situation may have been different. Quasi-stars, the hypothetical hybrids of black hole and star, are predicted to have reached sizes far beyond anything we observe today. Theoretical models suggest some quasi-stars may have grown to diameters of 50,000 or even 100,000 solar radii. At those scales, the star would extend well beyond the orbit of Pluto, swallowing the entire solar system many times over. A star 100,000 solar radii wide would have a diameter of about 430 billion miles. Our solar system, measured out to the edge of the Kuiper belt, is roughly 9 billion miles across. So a quasi-star at maximum size could fit our solar system inside it 48 times along its diameter alone. By volume, the quasi-star would contain hundreds of thousands of solar systems worth of space. These hypothetical objects existed only in the early universe. By the time galaxies began to form and stars settled into more familiar patterns, the conditions for quasi-star formation no longer existed. Some theoretical models also predict the existence of dark stars, a different kind of giant entirely. Dark stars are powered not by nuclear fusion, but by the annihilation of dark matter particles. If dark matter particles can annihilate each other, releasing energy in the process, that energy could power an enormous, puffy star made primarily of hydrogen and helium. Dark stars are predicted to have existed in the very early universe, possibly forming before any normal stars did. Some models suggest dark stars could have grown to sizes thousands of times that of modern hypergiants, possibly reaching diameters of millions of solar radii. A dark star at that scale would dwarf even quasi-stars. Its surface would extend far beyond the boundaries of our solar system, possibly even reaching out toward the nearest stars at the distances they sit today. The entire region of space we consider our cosmic neighborhood would fit inside one dark star with room to spare. Dark stars have never been observed. They remain entirely theoretical, depending on the nature of dark matter particles and their interactions, which are still poorly understood. If dark matter exists in certain forms, dark stars could have populated the early universe. If dark matter takes a different form, dark stars never existed at all. Even within the realm of currently known stellar physics, there are extreme objects that approach solar system engulfing sizes. Luminous blue variables, like Eta Carinae, can grow to enormous sizes during their unstable phases. Some pulsating yellow hypergiants briefly inflate to sizes that would push their atmospheres past the orbit of Jupiter and beyond. The point is that the universe seems capable of producing stars far beyond what we currently observe. The physics allows for it under the right conditions. The early universe likely contained giants that would dwarf anything we can find today. If our entire solar system could fit inside one star, that raises an obvious question. What conditions would even permit such a thing? And why do not we see stars like that anymore? The answer takes us back to the most chaotic place in any galaxy. At the center of every large galaxy sits a supermassive black hole. In the Milky Way, that black hole is called Sagittarius A star, and it contains about 4 million times the mass of our Sunday. It dominates the gravitational landscape of the central regions of our galaxy, pulling everything around it into wild, fast orbits. You might think the galactic core would be a great place to find massive stars. After all, the gas density near the center is high. Star formation should be easy. Plenty of raw material exists for building giants. The reality is the opposite. Supermassive stars do not survive near supermassive black holes. The reason comes down to two factors. First, the gravitational tidal forces near a supermassive black hole are intense. Tidal forces are differences in gravitational pull across an extended object. The closer side of an object feels stronger gravity than the farther side, and that difference stretches and tears the object apart. For a small object like a planet, the tidal force from a black hole is significant only when very close. For a giant star, the tidal forces become significant much farther out. A hypergiant orbiting near the supermassive black hole at the center of our galaxy would have its outer layers stripped away by the tidal forces, even at distances of millions of miles. Second, the radiation environment near a supermassive black hole is extreme. As matter falls into the black hole, it heats up and releases enormous amounts of radiation. Any star caught in that environment would have its outer atmosphere blasted away by the constant flood of high-energy photons. Hypergiants, which already have loosely bound outer layers, would be especially vulnerable. The combination of tidal stripping and radiation pressure means that the central regions of galaxies are essentially hostile to the largest stars. Smaller, denser stars can survive there, packed into tight orbits around the central black hole. But the loose, swollen monsters like Stephenson 2 to 18 cannot exist within a few hundred light-years of the galactic core. Astronomers have observed this directly. The center of our galaxy contains a remarkable population of massive stars, many of them only a few light-years from the supermassive black hole. These stars are mostly young, blue, and dense. They are not red hypergiants. Some of them have masses comparable to the biggest hypergiants out in the galactic disk, but they do not have the bloated, swollen sizes. The stars in the galactic core also live shorter lives than their counterparts farther out. The harsh environment accelerates their evolution. Material gets stripped away faster. Companion interactions are more common because stars are packed more tightly together. The end result is a galactic core full of dramatic stellar deaths and rebirths, but few of the truly enormous, low-density giants we have been touring. There is one famous exception. A star called S2 has been observed orbiting Sagittarius A star at incredibly close range, swinging within about 10 billion miles of the black hole during its closest approach. S2 is a massive star, roughly 15 times the mass of our Sun, but it is dense and compact rather than a swollen hypergiant. The fact that S2 can survive its close passes to Sagittarius A star tells astronomers something important about how stars adapt to extreme environments. Tighter, more compact stars handle the gravitational and radiation stress better than swollen ones. If a hypergiant ever did wander too close to a supermassive black hole, the result would be spectacular. The star would be torn apart in a tidal disruption event, its material spiraling into the black hole and producing a brilliant flash of radiation visible across millions of light-years. Stellar mergers offer another path to creating massive objects, sometimes producing stars that defy the normal categories. Stars do not always live alone. In fact, more than half of all stars in the galaxy are part of binary or multiple systems, with two or more stars orbiting each other in gravitational partnerships. Most of these partnerships last for billions of years, with the stars peacefully coexisting at safe distances. Sometimes, the partnership ends in collision. When two stars merge, the result is a new, larger object that combines the mass and angular momentum of both parents. The merger process is violent and chaotic, often ejecting significant amounts of material into space in the form of glowing nebulae. The newly merged star is typically more massive, hotter, and brighter than either of its parents, and it can have unusual properties that set it apart from normal stars. One famous example is V838 Monocerotis, a star that underwent a merger event in the year 2002. The event was observed in real time as the star suddenly brightened by a factor of 1 million over a few weeks, briefly becoming one of the most luminous stars in the entire Milky Way galaxy. As the merger event faded, the star left behind an expanding cloud of glowing gas that was later photographed by the Hubble Space Telescope, producing some of the most beautiful astronomical images ever taken. Stellar mergers can produce stars that are unusually massive for their type. If two large stars merge, the resulting object can exceed the typical mass limits for single stars formed by normal processes. These merger products may be one source of the very largest hypergiants observed in the modern universe. Some astronomers believe that Stephenson 2-18 itself may be the result of a stellar merger. Its size and properties are difficult to explain with normal stellar formation alone. A merger between two already massive stars, perhaps tens of millions of years ago, could explain how the star reached its current absurd dimensions. Mergers also play a role in producing certain types of supernovae. Some supernovae have unusual properties that match what would be expected if the progenitor star had recently merged with a companion before exploding. The merger may have stirred up the star's interior, accelerated its evolution, or changed its chemical composition in ways that affected the eventual explosion. The most extreme stellar mergers involve compact remnants like neutron stars and black holes. When two neutron stars merge, the event produces a brief but incredibly powerful burst of gravitational waves, which can be detected by observatories like LIGO and Virgo on Earth. The merger also creates a kilonova, a flash of light that contains the chemical signature of newly forged heavy elements like gold and platinum. Neutron star mergers are now believed to be the primary source of the heaviest elements in the universe. The conditions during the merger are so extreme that they can synthesize elements that even supernovae cannot produce in significant quantities. The gold in your wedding ring, the platinum in a catalytic converter, the uranium in nuclear power plants, all of these elements come primarily from neutron star mergers happening across cosmic time. If a neutron star and a black hole merge, the result is even more dramatic. The black hole tears the neutron star apart through tidal forces, then swallows the debris. A flash of gravitational waves and electromagnetic radiation marks the event, and a slightly larger black hole is left behind to drift through space. Stellar mergers add another layer of complexity to the question of how big stars can get. Through mergers, stars can briefly exceed the size and mass limits that normal stellar evolution would impose. These hybrid monsters live short, dramatic lives before exploding or collapsing into final remnants. Beyond the realm of normal stars and their mergers lies a hypothetical category of objects that might be the strangest of all. About 85% of all matter in the universe is invisible to us. We call it dark matter, and we know it exists because of the gravitational effects it has on galaxies, galaxy clusters, and the structure of the cosmos as a whole. But we have never directly observed a dark matter particle. We do not know what it is made of. If dark matter consists of certain types of particles, then in the very early universe, those particles could have powered a strange kind of star. Astronomers call these hypothetical objects dark stars, and they would be unlike anything that exists today. A dark star would not be made primarily of dark matter. The bulk of its material would be ordinary hydrogen and helium, just like normal stars. The dark matter would be present in much smaller amounts, but it would play a critical role in keeping the star going. The mechanism behind a dark star is annihilation. If dark matter particles meet their antimatter counterparts, they would annihilate each other, releasing energy in the process. In a region of space where dark matter is densely concentrated, the rate of these annihilation events could be high enough to provide significant amounts of energy. Inside a dark star, dark matter would be concentrated near the center, where gravity has pulled it inward. The annihilation events would heat the surrounding gas, creating an outward radiation pressure that supports the star against gravitational collapse. The star could remain stable for as long as the dark matter supply lasts. Without normal nuclear fusion, dark stars would not need to be hot in the same way that conventional stars are. The temperatures inside a dark star could be much lower than in a conventional star of similar mass. Lower temperatures mean less efficient cooling and less compact structure. Dark stars would therefore be enormous, possibly far larger than any conventional star. Some theoretical models suggest dark stars could have grown to sizes of millions of solar radii, with masses of millions of times that of our Sun day. At those scales, a single dark star would be larger than entire solar systems and contain enough material to form thousands of normal stars. They would be the largest individual objects the universe has ever produced. Dark stars would also have lived for very long times by stellar standards. With dark matter as a slow-burning fuel source, a dark star could remain stable for hundreds of millions or even billions of years, far longer than even the smallest conventional stars. They would have been long-lived monsters dominating the early universe. The end of a dark star would come when its dark matter supply ran out. Once annihilation could no longer support the star against gravity, the structure would collapse. Some of the collapsing material would ignite normal nuclear fusion, briefly turning the dark star into a conventional star or supernova. The rest would fall into a central black hole. The black holes left behind by dying dark stars would have been massive, possibly providing the seeds for the supermassive black holes that sit at the centers of galaxies today. This is one possible explanation for how supermassive black holes grew so quickly in the early universe. They may have started as the cause of dying dark stars. We have no direct evidence that dark stars existed. Their existence depends entirely on assumptions about the nature of dark matter that have not yet been confirmed. If dark matter consists of weakly interacting massive particles that can annihilate, dark stars are theoretically possible. If dark matter takes some other form, dark stars never existed. The James Webb Space Telescope and other future observatories may eventually find evidence of dark stars by detecting their unusual chemical signatures or thermal properties in the very early universe. Until then, dark stars remain a fascinating possibility in the theoretical landscape of cosmology. How big could a star theoretically grow if all the laws of physics work together to allow it? Physics has limits. Some of those limits are practical, like the Eddington limit, which depends on the specific properties of the star in question. Others are more fundamental, set by the basic structure of spacetime and the laws of gravity. To find the absolute maximum possible size of any star, we need to consider both kinds of limits together. Start with the Eddington limit. This is the boundary where radiation pressure from a star's core equals gravitational pull, and beyond which the outer layers cannot stay attached to the star. For ordinary stars with modern chemical compositions, the Eddington limit caps masses at around 150 solar masses. For early universe stars made of pure hydrogen and helium, the limit is higher, possibly up to several hundred solar masses. Once a star reaches its mass limit, its size depends on its evolutionary state. A young, hot, blue star compresses itself into a relatively small volume because high temperatures keep the gas from expanding too much. As the star ages and cools, its outer layers puff up dramatically. By the time the star reaches the red supergiant or red hypergiant phase, it has grown to enormous size, possibly 2,000 solar radii or more. That gives us a maximum size for normal stars of about 2,000 solar radii. Stevenson 2 to 18 sits right at that limit. Now consider quasi-stars. These hybrid objects, with black holes at their centers, can grow much larger than normal stars, because the energy source is different. A black hole feeding on infalling matter can produce energy at rates far exceeding what nuclear fusion delivers. The radiation pressure can support a much more swollen outer envelope. Theoretical models suggest quasi-stars could reach diameters of 100,000 solar radii, or possibly more. That is a 50-fold increase over the largest known normal stars. A quasi-star at that size would have a diameter of about 430 billion miles, comfortably containing the entire solar system many times over. Dark stars push the limit even further. If dark matter annihilation provides a slow, steady energy source, the resulting star could be larger and longer lived than any normal star or quasi-star. Theoretical estimates for dark stars range up to millions of solar radii. At that size, a single dark star would be larger than the typical distance between stars in our galaxy, meaning it could contain entire stellar neighborhoods inside it. Beyond dark stars, the question becomes whether any other kind of object could grow larger still. The answer brushes up against fundamental physics. If you tried to build something the size of a galaxy out of gas and call it a star, gravity would not let you. The material would either fragment into many separate smaller stars, or it would collapse into a black hole before it could maintain a stable, glowing structure. The mass required for any object to behave like a coherent star is limited by the conditions needed for either nuclear fusion or some other steady energy source. There is also the issue of how light travels across enormous distances. A star 10 million solar radii wide would have a diameter so large that light could not cross it within a reasonable time. Light from one side would take days to reach the other. Internal communication within the star, in the form of pressure waves and radiation transport, would become so slow that the star would have trouble holding itself together as a single object. It would behave more like a loose cluster of glowing material than a coherent star. The practical maximum for any star, accounting for all these factors, is probably around millions of solar radii, achieved only by hypothetical objects like dark stars. Anything larger than that loses the structural coherence that defines a star. What does the light from these monsters tell us by the time it finally reaches Earth? Light is fast. In 1 second, it travels nearly 186,000 miles. In 1 year, it covers about 6 trillion miles, a distance astronomers call a light year. Light is the fastest thing the universe knows how to make, and for everyday purposes, it seems instantaneous. For cosmic distances, light is slow. The light from Stephenson 2 to 18 takes about 20,000 years to reach Earth. The light arriving at our telescopes tonight left that star around the same time humans were just beginning to develop agriculture. Whatever was happening at Stephenson 2 to 18 20,000 years ago is what we are seeing now. The star's current state is unknown to us. It will not be observable until our descendants, 20,000 years from now, see today's light arrive. This delay means that the night sky is essentially a time machine. Every star you see is a time capsule, showing you a snapshot of how the star looked when its light began its journey. The closer the star, the more recent the snapshot. The farther the star, the older the image. Sirius, only 8.5 light years away, shows you light from less than a decade ago. Betelgeuse, 640 light years away, shows you light from the late 1300s. Stephenson 2 to 18 shows you light from the dawn of human civilization. And distant galaxies, billions of light years away, show you light from when the universe was much younger than it is today. For the most extreme stars, this time delay becomes haunting. Some hypergiants we observe today may have already exploded as supernovae thousands of years ago. The light from their explosions has not yet reached us. We are watching ghosts, stars that no longer exist in their current form. When a hypergiant like Stephenson 2 to 18 finally explodes, the light from the explosion will travel for 20,000 years before reaching Earth. By the time we see it, the star itself will have been gone for 200 centuries. The supernova remnant will already have expanded to enormous size, and the dust shells around the original star will have been swept up by the shockwave. But during the moment of arrival, the explosion will be spectacular. A new bright point will appear in the constellation Scutum, possibly visible during daylight. Over the following weeks, the new star will fade from peak brightness, eventually dimming below naked eye visibility. The whole show will last for months. For supernovae closer to us, the effects are even more dramatic. A supernova within a few hundred light years of Earth would briefly become as bright as the full moon, casting shadows at night and remaining visible during the day. The last such event recorded in human history was in the year 1054, when a supernova explosion in the constellation Taurus was observed by Chinese astronomers. The remnant of that explosion is now the famous Crab Nebula. The light delay also means that we have no way to predict supernovae in real time. If Betelgeuse explodes tonight, we will not know about it for 640 years. The signal will arrive at the speed of light, but no faster. There is no early warning system, no faster-than-light communication that could tell us what is happening at distant stars right now. The night sky is not a snapshot of the present universe. It is a layered tapestry of moments stretching back through history. Every light that hits your eye is a postcard from a different time and place, sometimes recent, sometimes ancient, often from objects that no longer exist as they appeared to us. What gets left behind when these monsters finally die? When a hypergiant explodes, the visible aftermath is dramatic but brief. The supernova lights up the sky for weeks or months before fading. The expanding cloud of debris drifts outward through space at thousands of miles per second, glowing as it pushes through the surrounding interstellar medium. But the explosion is not the end of the story. Hypergiants leave behind permanent marks on the universe, scars that persist for billions of years. The most visible legacy is the supernova remnant. As the expanding cloud of debris from the explosion plows into surrounding gas and dust, it heats and compresses the material, creating glowing structures of incredible beauty. These remnants can stretch for hundreds of light years and persist for tens of thousands of years before slowly fading. Some of the most beautiful objects in our sky are supernova remnants. The Crab Nebula, the Veil Nebula, the Cygnus Loop, and many others are the lingering aftermath of stars that died long ago. Each one tells the story of a hypergiant or supergiant that completed its life cycle in a brilliant flash and is now leaving its mark on the galaxy. Many supernovae also leave behind a compact remnant at their center. For most explosions, the leftover core becomes a neutron star, a city-sized sphere of ultra-dense neutron matter. Neutron stars are weird objects. They contain about 1.5 times the mass of our Sun packed into a volume only about 12 miles across. A teaspoon of neutron star material would weigh several billion tons on Earth. Neutron stars often spin rapidly, sometimes hundreds of times per second. As they spin, their strong magnetic fields produce beams of radiation that sweep across space like cosmic lighthouses. When one of these beams happens to point at Earth during each rotation, we detect it as a regular pulse of radio waves. Stars in this configuration are called pulsars. For the most massive stars, including hypergiants like Stephenson 2 to 18, the leftover core does not stop collapsing at the neutron star stage. It continues compressing until it forms a black hole. A black hole is a region of space where gravity is so intense that not even light can escape from inside it. Black holes from stellar collapse typically contain a few times the mass of our Sun, packed into a volume so small that the gravitational field becomes overwhelming. The boundary around a black hole, called the event horizon, marks the point of no return. Anything that crosses inside the event horizon falls toward the central singularity and never comes back out. The black holes left behind by hypergiants drift through space, sometimes alone, sometimes in binary partnerships with other stars. We have detected many of these stellar mass black holes over the years, often by observing the X-rays produced when a companion star's material falls into the black hole and heats up to extreme temperatures before crossing the event horizon. Beyond compact remnants, hypergiants leave behind a chemical legacy. The heavy elements forged in their cores and in the explosions that ended their lives get scattered across space and mixed into the surrounding gas clouds. This enriched material eventually forms new stars and planets. Every atom of carbon in your body, every bit of oxygen you breathe, every drop of water you drink, every gram of iron in your blood traces its origin back to stars like the ones we have been touring. The carbon was forged in red giants. The oxygen and silicon were made in massive stars. The iron was produced in the cores of supergiants and scattered by supernovae. The gold and uranium and other heavy elements came from neutron star mergers and the most extreme explosions. You are made of star stuff, and much of that star stuff came from giants whose names you have heard in this journey. But the biggest star ever to exist may not yet have been discovered. Throughout this journey, we have visited some of the most extreme stars known to exist. Stephenson 2 to 18 currently holds the title of largest confirmed star, sitting at about 2,150 solar radii. Its volume could contain 10 billion of our suns. Its size puts it right at the theoretical limit imposed by the laws of physics for normal stars. But Stephenson 2 to 18 may not actually be the biggest star out there. The catalogue of known hypergiants represents only a tiny fraction of the stars in our galaxy. The Milky Way contains hundreds of billions of stars, and only a small percentage have been studied in detail. Many of the largest stars are hidden behind dust clouds, obscured by the structure of the galactic disk, or simply located in regions of space that have not been thoroughly surveyed. There are likely dozens, possibly hundreds, of red hypergiants hiding in the Milky Way that have not yet been identified. Some of them may be larger than Stephenson 2 to 18. The hunt for these hidden giants continues with each new generation of telescopes and surveys. Beyond our galaxy, the situation is even more open. The Large Magellanic Cloud contains WOG 64, a hypergiant we visited earlier. The Andromeda Galaxy, our nearest large galactic neighbor, almost certainly contains many massive stars that have not been studied in detail. And then there are the billions of other galaxies in the observable universe, each with its own population of giants, most of them too far away for detailed observations. Future telescopes may rewrite the leaderboard entirely. Instruments like the James Webb Space Telescope, the Vera-C, Rubin Observatory, and the upcoming Extremely Large Telescope are designed to peer deeper into the universe than ever before. They will survey vast numbers of stars in unprecedented detail, possibly revealing hypergiants that dwarf anything currently known. Ground-based interferometry projects, which combine the light from multiple telescopes to act as one giant telescope, are making it possible to actually resolve the disks of distant supergiants. For the first time, astronomers can see the surfaces of these stars rather than just measuring them as points of light. Future observations may directly image hypergiants in the Magellanic Clouds and other nearby galaxies, revealing their true sizes with much better precision than current methods allow. There is also the possibility that conditions in certain regions of the universe still allow for stars larger than Stephenson 2 to 18 to form. The early universe certainly produced larger stars, including quasi-stars and possibly dark stars. The current universe, with its enriched chemistry and crowded star-forming regions, may not be entirely incapable of producing extreme objects. Rare, exotic stars could exist in unusual environments. The question of the largest possible star is also tied to the question of the largest possible mass. Theoretical physics has explored this question for decades, with most models suggesting an upper mass limit of a few hundred to maybe 1,000 solar masses for any single star. But theoretical limits have been revised many times as new physics becomes understood. The maximum mass and size of stars are still active areas of research. We may never identify the absolute largest star in the universe. The cosmos is too vast, with too many stars hidden across too many galaxies for any complete survey to be possible. But every new discovery pushes the boundaries of what we know is possible. Every new measurement refines our understanding. And every new generation of astronomers will inherit a leaderboard that has shifted from the one their teachers knew. The biggest star ever to exist may still be hidden, somewhere in the vastness of space, waiting to be discovered. Or perhaps it died billions of years ago, and only its scattered remnants and the ripples it left in space-time survive as evidence of its passing. The universe is bigger than your imagination. The stars that fill it are bigger than your imagination, and the search for the largest of them all continues, one observation at a time, as humans look up at the night sky and try to understand the scale of what they are seeing.